In this lecture, I'm going to discuss about the EDC main topics, or we can say formulas. Generally, what we are getting regularly in the GATE exam, right? So I'm starting with the first topic, that is energy bands in intrinsic and extrinsic silicon. So we need some basic formulas. From these basic formulas, we'll get at least 50% of the questions in the GATE. So first the formula required is thermal voltage. So thermal voltage, generally in the all questions we need to use this thermal voltage. So it is generally KT by Q or K bar T by Q. So what is this? K is Boltzmann constant. If it is in electron volts per Kelvin, so it is 8.62 into 10 to the power minus 5. If it is in joules per Kelvin, it is 1.38 into 10 to the power minus 23. Or I can use directly this type of expression also. If I substitute this K bar at this Q, so this is T by 11,600 volts. So by using, if we want to find at T equal to 0 degree Kelvin, so substitute T equal to 0, so we will get 0. At 300 degree Kelvin, substitute 300 degree Kelvin, we will get 26 millivolts approximately, or we can say it is 0.0259 etc. right volts. So this is the thermal voltage required. In the exam he may ask what is the thermal voltage at 200 degree Kelvin. So substitute here, then we can find. Now one more, it's a very important one, is charge of an electron or charge of a hole. It is fixed, that is 1.6 into 10 to the power minus 19 coulombs. So for electron it should be minus, for a hole it should be plus, right? Next topic or next concept here is energy gap. So generally, if we take any semiconductor, metal or insulator, there is a conduction band, there is a valence band. What is this conduction band? Whenever in this conduction band there is electrons, we can say we can get a conduction of current. So if valence band is, it will be filled with the holes. Generally it will be empty. The moment it is filled with the electrons, the conduction will start, right? That is enough for the sake of formulas. So the gap between this conduction band and valence band is called energy gap, right? So if this energy gap is very high, so that is not in that condition there is not possible of the conduction, right? So we are having the semiconductors or germanium silicon. So for germanium and at 0 degree Kelvin, so this energy gap is 0.785 electron volts. For silicon at 0 degree Kelvin, 1.21 electron volt. Similarly at 300 degree Kelvin, it is 0.72 electron volts, and for silicon it is 1.1 electron volts. So many times in the exam they asked what is the energy gap at 300 degree Kelvin for silicon, or energy gap for 300 degree Kelvin for germanium, etc. Sometimes they may ask if temperature is increasing, what happens to energy gap? So energy gap is inversely proportional to temperature, right? So if you increase the temperature, energy gap will decrease. So for that I need these two expressions. If you remember, you may get, suppose find the energy gap of silicon at 300 degree, not to 200 degree Kelvin. So if you use this formula, you can directly get that energy gap. So for silicon, Eg0, that is energy gap at 0 degree Kelvin. So this is 1.21 minus 3.6 into 10 to the power minus 4 into temperature. If we increase temperature, this value will increase. So Eg0 will suppress from this one. So we will get decreased one. Similarly, for germanium, Eg0 is equal to minus 2.2 into 10 to the power minus 4 into T electron volts for germanium. So by substituting some temperature value and Eg0 values, so we can get different temperature and different Eg values. Now if we see what is this energy gaps in metal or insulator or semiconductors, so it will look like this. In metal, so we are having so many number of free electrons, right? So many. So that means conduction band and valence band will be overlap. That is, it is ready to conduct, right? So examples I can say copper and gold, etc. See, this overlap is in proportional to temperature. That is, if you increase the temperature, this overlap also will increase. That means the conduction band will fill with very high number of electrons. If you see the insulator, the energy gap is very large. So in electron volts terms, it is greater than 5 electron volts, sometimes 6 electron volts. Right? Examples we can say air and diamond, or we can say the wood also. Now similarly for the semiconductor conduction band and valence band will be somewhat the gap will be small, right? It may be 1 electron volt. So we have seen that is 1.1 electron at 300 degree Kelvin, etc. So but at 0 degree Kelvin, all semiconductors behaves as insulator. So we have to remember this point also. They may ask directly, right? At 0 degree Kelvin, what is germanium semiconductor behaves? So it's like a insulator only. But if we increase the temperature at 300 degree Kelvin, the conduction band, this is conduction band and this is valence band. So the conduction band will have here empty, but here we will have some electrons in the conduction band. That means it is start conducting. And the moment we are having these electrons here, it will have the holes. How many number of electrons here? Same number of holes also will be here. Now examples we can say silicon and germanium. This is about some energy gaps. Next one is a very important the formula, electric field intensity. That is, so this is capital E, or this is one more notation we can use also, right? This is not small. There is a difference between epsilon or what do you call that is permittivity. This is the different notation like this, electric field, that is minus dV by dx, right? Or we can say if we take mod dV by dx, or directly we can say volt per the length, voltage per unit length, that is volt per meter. Always we will get sometimes we got questions, find the electric field if we apply some volts per some length per 1 centimeter also, right? So this is electric field intensity formula. Next topic is mobility of charge carriers, that is mu. So mobility is like how much speed or how much fast the electron or holes are moving, right? So mu is equal to drift velocity by electric field. V, drift velocity, is electric field, mu is mobility. So V is equal to mu into electric field. So what is this drift is? If you apply some electric field, right, how much fast the electron is moving, that is a mobility. So we need some standard values for germanium, and it will have electron as well as hole mobility. Silicon, electron and hole mobility. So it is fixed, right? Sometimes in some books they will follow 3900, 1900, 1350, 480, etc. But that variations can possible. But we can remember this mu n 3800 centimeter square by volt second. So sometimes in the gate they will ask directly, what is the germanium electron mobility, what is the germanium hole mobility, etc. So 3800 centimeter square by volt second. This units must be remembered. Sometimes they may ask in meters per volt second. So we need to convert. So 3800 is first in centimeter square per volt second, and for mobility hole mu p 1800 centimeter square by volt second. Similarly silicon 1300 and 500. But sometimes they ask what is the difference, depends on the temperature. It is inversely proportional to T power generally T power m. So if it is the numerator, so it will become mu is directly proportional to T power minus m. That is, if you increase the temperature, mobility will decrease, right? And similarly mobility and the electric field, if you draw the graph, so mu is for a small electric field it will be constant, then for large like this it will be inversely proportional to root E. But if you very high fields, it is inversely proportional to E. So that we need to remember, right? So it is somewhat linear, inversely linear, but here it's like a what you call parabolic, inversely proportional. That is, if E is increasing or somewhat, so it will decrease very slow, but here it is decreasing very fast. So this curve also we need to remember. Next one is Tiptoe velocity. How is the relationship between this electric field? So this is for ideal case, but if we say V is equal to mu E by 1 plus mu E by Vs, if for high electric fields, so one will be neglected, so mu E with V cancel, it will become Vs. So this Vs is generally called velocity of saturation. Similarly, this electric field, that is volts per centimeter or kilovolts per centimeter, if you are increasing the electric field slowly, initially it will increasing with the linear, then sublinear, then almost getting constant. That is called velocity of saturation. You have to remember this formula also, right? The next topic is very important topic is Einstein relationship, right? So this is depending on the mobility and thermal voltage and diffusion constant. D by mu is equal to Vt, that is thermal voltage. If we relate with the mobility electron, so dn by mu n or dp by mu p for holes, which is equal to Vt. Again, diffusion constant units are centimeter square by second or meter square by second. So we can find directly what is the diffusion constant for electrons for germanium, that is mu n into Vt. We know mu n 3800 centimeter square by volt second, and Vt is 26 millivolts at 300 degree Kelvin. So if you substitute, and you will get 99 centimeter square by second, and for holes 47. Similarly for silicon, dn is 34 centimeter square by second, dp 13. Extrinsic semiconductor, some basics. So in intrinsic semiconductor, generally the number of free electrons will be equal to the number of holes, right? So generally represented by N is equal to P is equal to Ni. Ni is generally it is called intrinsic concentration, which is equal to number of holes, which is equal to number of free electrons, right? So what is the some relationship between this energy gap temperature is Ni square is equal to A naught into T cube into e power minus Eg by Kt. Sometimes they may ask, so intrinsic semiconductor, is it a when temperature increases, intrinsic semiconductor either increases or decreases, etc. So by this expression we can find the some relationship between the Ni and Eg and temperature. Next one is, what is the intrinsic concentration in germanium? So we are having two types of semiconductors, germanium and silicon. In germanium it is 2.5 into 10 to the power 13 per centimeter cube. In silicon it is 1.5 into 10 to the power 10 per centimeter cube. Sometimes in the question they will mention this intrinsic concentration, sometimes they don't. So we need to remember these two values. Next one is, generally we have to use this mass action law in some problems in gate. So what is that is N into P, that is free electron concentration into hole concentration is equal to Ni square. Always we have to use this one. You have to remember the mass action law. Now let's discuss the extrinsic semiconductor. In extrinsic semiconductor there will be two types. So one is p type semiconductor and n type semiconductor. Generally extrinsic is we will say it's a impure semiconductor. Intrinsic means this is a pure semiconductor. So that's why the number of holes and electrons will be equal, right? So in p type semiconductor, how to make p type is, for the intrinsic semiconductor we need to add some doping elements. So when you are adding third group element, that is boron, aluminum, gallium, so it will become p type semiconductor. Generally it is called acceptor concentration. That means it will accept some electrons because it will provide some holes. That is, we have to go in deep, but what my intention for this videos is, it's like a just recap. So what is the formulas, what is the simple theory, that's it. So generally it is called Na, acceptor concentration. Similarly for n type doping elements, that is phosphorus, arsenic, antimony, some bismuth also, and this is generally it is called donor concentration because it will provide the free electrons, so more, so it will donate. That is called, it's a donor concentration. Generally it is called Nd. Next we need to, sometimes they will ask, the GATE 2016 the question comes like this. So energy band diagrams in n type as well as p type. So this is for n type semiconductor. See, energy
this energy band, that is conduction band and valence band, there is a EC, that is energy, what is the highest level energy, that is EC, conduction band energy level. Similarly, valence band energy level EV. Now when we are doping, so there is a one more level that is called donor level, ED. In this level there is some electrons. Then when we apply some small voltage, that will be transferred to the conduction band, these electrons. This gap we should remember, that is 0.0 n electron volt for silicon, 0.05 volt electron volt for germanium. If it is a p-type semiconductor, the acceptor level is nearer to this voltage valence band level, energy level, that is EV. So it is called an acceptor level. Similarly, the energy gap between these two will be 0.01 electron for silicon, 0.05 electron for germanium. This question came in the GATE 2016. This energy band is given, and tell that which type of semiconductor is this. You can verify, right? So this is about this energy band diagrams for N-type as well as this is for P-type semiconductor. Next concept we have to take is N-type semiconductor. In N-type semiconductor, what are the majority carriers? So this is generally electrons. Minority carriers, it is holes. Similarly, majority carriers in P-type semiconductor are holes. Minority carriers are electrons. The notations are majority is P, it is holes, so it is acceptor concentration. Similarly, for N-type, it is ND. Now using mass action law, so NP is equal to Ni square. If you take N-type semiconductor, this will be represented by like this: N-type, N-type. So number of electrons and number of holes in N-type, which is nothing but Ni square. So if we know Nn, that is this Nd, I can find the Pn, that is minority carriers in N-type semiconductor, as Ni square by Nn or simply Ni square by Nd. Similarly, for P-type semiconductor, we can find the minority carriers in P-type semiconductor is equal to Ni square by Na. This is called minority carrier, that is electrons in P-type semiconductor. Similarly, here the holes in N-type semiconductor. So generally, most frequently we will get questions from these formulas only, right? Next one we need to find is, what is this resistivity? We will see conductivity first, then we will go about the resistivity. Resistive formula is like simple ohm centimeter or ohm meter, units ohm meter, right? Now this is rho, represented by resistivity is rho is equal to capital R. This is a resistance. R is the resistance of that material, resistance, and L is the length of that material, and A is the cross sectional area, right? So frequently we have to use this formula also. Similarly, for conductivity, conductivity is nothing but the reciprocal of the resistivity, or 1 by ohm, units are 1 by ohm centimeter or 1 by ohm meter, or we can say Siemens per centimeter or ohm centimeter per inverse also generally, right? Now what is this conductivity is? This is the electron concentration, this is charge, and this is a mobility. This is for metals, and I will recall in metals majority carriers is electrons. So generally always in metals only electrons will be there, so that's why the conductivity is NQ into mu. If it is an intrinsic semiconductor, this is the formula: sigma I is equal to Ni into Q. In intrinsic semiconductor, there will be equal number of holes and electrons, but the mobilities will be different. That's why Niq into mu n plus mu p. If it is an extrinsic semiconductor, so it will become Nq mu n plus Pq mu p. So we have to remember, at least you will get one question. So we are getting so many sets in the gate, so at least in one set you will find the conductivity, or find the mobility, or something, anything. What is the ratio between mu n by mu p, so etc. will get. So we have to remember these formulas, right? The next concept is the current density. So current density is nothing but current by per area, amps per centimeter square or amps per meter square. So what is this formulas we have to use? This is generally we will find in Ohm's law. in network theory, J is equal to sigma into electric field. It is conductivity and this is electric field. So for metals, if you find the sigma is equal to NQ mu1, this is metals. If it is a semiconductors, we have to go for NQ mu1 plus PQ mu p into E. That is, we already discussed the sigma. But at equilibrium, this formula is also sometimes necessary. ND plus P, that is, this is a donor. Whenever some electron is donating, it will become positive ion. So positive plus holes will also positive charge. So positive plus positive should be equal to the accept ion. Whenever some metal or anything accepts, means it will become negative. So negative plus electrons is also a negative charge only. So negative plus negative. So this should be equal. Positive is equal to negative. That's why ND plus P is equal to Na plus N. But if we consider N-type semiconductor, so Nd is a donor concentration, is nothing but electron concentration only. When D is very much greater than Na, that means I can neglect Na and P. So Na will become directly Nd. Similarly, for P-type semiconductor, Na is very much greater than Nd and P. So we have to neglect this Nd and N. So P approximately Na. So what is this meaning is, this is a majority concentration, this is a minority. So it is very much high compared to this minority carrier concentration, right? So these formulas are necessary. I mean, you have to remember these formulas. At least we will get one question or two questions, so depending on the sets, right? And the next concept, that is diffusion and drift. Diffusion and drift currents in semiconductor. So first we'll discuss diffusion. Diffusion is a migration from higher density to lower density. So higher density means, so suppose it is having some electrons or holes here, very high concentration. So diffusion means these carriers will diffuse from higher to lower. So after some time it will be at equilibrium. So that's why, so suppose this is the length L, and if I dope here so many number of electron holes, it will slowly diffuse. It's a very simple. So if we take a glass of water like this, so many, the molecules will be there. If we drop ink, so the moment when we drop, it will be very density will be very high, then slowly it will dissolve in the water. So that is like a diffusion only. Similarly, the diffusion is migrating the carriers from higher concentration to lower concentration. So when this is happening, we will have some gradient, that is d by dx. So what is electron concentration gradient is dn by dx. So what is the, suppose it is having some 10 to the power 6 here, and it is having 10 to the power 2 only. So what is the difference? I can get 10 to the power 6 minus 10 to the power 2 by, so what is the length of this? We can say length of the diffusion, right? That is dx. So electron concentration is dn by dx, hole concentration gradient is dp by dx. So what is the length of the diffusion is, I can remember directly, L is equal to root of d into tau. We may get problems directly from this also. Find the diffusion length if a diffusion constant is given and the time carrier time is given something. So if it is electron, I can get Ln is equal to root of dn into tau n. Hole is Lp is equal to root of dp into tau p. So dn is diffusion constant. It is in centimeter square by second units. So electron means dn, holes means dp. Similarly, carrier lifetime. So tau n and tau p, for this is for electrons, this is for hole, right? So now whenever there is a electrons are moving or diffusing from higher to lower, then what we can get is, whenever there is a movement of electron or hole, we will get a current, right? So what is the diffusion current density, right? So generally we will say, we will take a semiconductor bar with cross-sectional area and what is the length of that. So that's why we will get first diffusion current density, that is Jn. So this is electron concentration, electron charge, that is minus q into diffusion constant dn into dn by dx. Now minus q is for the negative charge, and what about the dn by dx? Suppose this is the length, x is equal to 0 and this is x is equal to L. What is the difference I will get is, 0 minus L, so minus L. So diffusion length, or we can say it is negative. dn is, if it is 10 to the power 6 here or 10 to the power something, so that difference I can take directly dn. But we will start from x is equal to 0 to x is equal to L, then I learn negative. So that's why always for our electron diffusion current density q into dn by dx. Similarly, if I write for holes, that is jp is equal to plus q into dp into d by dx. So dx is a negative, so I will get minus q into dp into dp by dx. This is for electron current density, and this is for hole current density in diffusion only, right? So these two equations are very important, you have to remember. So we will get directly question from these two equations also. Next one is drift. So what is a drift is, so generally drifting means by applying some force or external force, electric field generally in the terms of EDC. If carrier is moving, then it is called a drift. So whenever carrier is moving, the current will be developed, that is a drift current. So diffusion is simply if a carrier is moving from higher concentration to lower concentration, that is diffusion. Now drift means we have to apply some external force, right? That is a drift. So what is drift current density is J is equal to sigma into E, right? So this is applied electric field, so that is directly proportional to electric field. So it's like a Ohm's law, right? So then this sigma is conductivity. So if I draw for Jn, that is electron drift current density, that is sigma n into E. What is sigma n? We have discussed already, nq into mu n. Similarly Jp, pq into mu p into E. E is applied electric field. Now if I write total current density, that is Jn, so it will have diffusion as well as drift. So Jn is equal to nq into mu n into E plus q into dn by dx. Similarly for whole total current density, drift current plus diffusion current, so pq mu p into E, this is for minus q, so I will get like this. So by these expressions also we can get sometimes the problems. Now we'll see one or two problems. We can do so many problems, previous gate problems, right? So this was the one of the gate problem. A silicon sample is uniformly doped with 10 to the power 6 phosphorus atoms, and 2 into 10 to the power 16 per centimeter atoms per centimeter cube with boron. So if all the dopants are ionized, the material is, so we have to find what material it is. So phosphorus means that is a N type, or we can say electrons are increasing the doping, so that is why I have taken Nd is equal to 10 to the power 16. So boron means it is a P type, so or we can say acceptor impurities, though I have taken Na is equal to 2 into 10 to the power 16. If we compare these two, Na is greater than Nd, so I can easily tell that it is a P type semiconductor. Now he mentioned if all the dopants are ionized, that means 1 into 10 to the power 16 and this 1 into 10 to the power 6 to, so it's having 2 times of 10 to the power 16. So this one time and this one time will be ionized, then remaining is 1 into 10 to the power 16. So that's why the overall electron concentration of that material is Na minus Nd, that is 10 to the power 16 atoms per centimeter cube, and it is a P type semiconductor. Now why I have taken the difference is, so a silicon sample is uniformly doped. So a silicon semiconductor is there, then it is doped with 10 to the power 16, and then remaining doped with 2 into 10 to the power 16. So 1 into 10 to the power 16 boron and 1 into 10 to the power 16 phosphorus will ionize, then the remaining will become 1 into 10 to the power 16, that is P type semiconductor concentration. Now this is the 2016 recent question. So what we discussed about this diffusion drift, depending on that concept. The figure shows below the doping distribution in a p-type semiconductor in logarithmic scale. The magnitude of the electric field in kilovolt per centimeter in the semiconductor due to non-uniform doping. So this concept is depending on the drift as well as diffusion. What is the meaning is, the moment electric field is coming, it is also including some drift. Now what how to do this problem is, so this is a p-type semiconductor because it is a given in here is Na, that is acceptor impurity concentration. So I will go for the whole total current density, that is Jp, drift as well as diffusion. Now so he said non-uniform doping, right? So in non-uniform doping, both the drift will oppose the diffusion. So whatever the force applying due to diffusion, it will oppose the drift will oppose the diffusion. So that's why in non-uniform doping they both will be equal. That means if they both are equal, it will become zero. What is the reason? For Jp, generally the Jp was minus q into dp by dx, right? So if I substitute minus Jp here, so it is should be cancel each other, then this should be both are equal, then only it will be cancelled, right? So actually this was minus, I should be minus, right? Then it will be equal, so it will be cancelled. Now what is JDP drift? Sigma p into E is equal to q into dp by dx. So p sigma, I can replace p q mu p into E is equal to q into dp by dx. Q can be cancelled. So what is E? dp by mu p into this 1 by p, that is concentration, into dp by dx. So from the mathematics, so what is the differentiation of ln log? So 1 by p into dp by dx. So I can replace this term with d by dx of ln into p. Now from the diagram, he mentioned for at 1 micrometer this is 10 to the power 15, at 2 micrometer this is 10 to the power 16. So what I have to replace? At 2 micrometer it is 10 to the power 16, at 1 micrometer it is 10 to the power 4. So I can substitute here. So ln A minus ln B, so it will become ln of A by B. So 10 to the power 16 by 10 to the power 14, so 10 square. 2 minus 1 1. It is in micrometer. So micrometer is 10 to the power minus 16, it should be converted into centimeters, so 100 centimeters. What is this dp by mu p from the Einstein relationship? So d by mu is equal to Vt, thermal voltage. So I can replace 26 millivolts. So if you solve this, I will get 1197.3 volt per 3 volt per centimeter. But he mentioned in kilovolts, so it should be converted 1.197 kilovolt per centimeter, right? So again I am explaining, in non-uniform doping, the diffusion will opposed by the drift always. Suppose if you see this, suppose it is constant, right? So what is the difference? Dn, it will become 0, so there is no diffusion at all, right? But whenever there is a diffusion and when you apply some electric field, that electric field opposes the diffusion. So that's why the diffusion and the dip should be equal, right? So this is how we got the answer. So this type of questions will come in the regular basis, right?